I want to start with apologizing to my for switching my talk. Right, I was originally, if you check, it was a different one, and thank my apologies to my co-authors because I believe they were expecting me to talk about other things. However, probably most of you know it, but like to explain myself, I have to say I'm Ukrainian, and last 2 months have been quite difficult for me. So I can do right now very basic things. So I switched to the talk I'm most comfortable with, right? So I will be talking about representation of Jordan algebras and superalgebras. And I'm sorry for those who probably already have listened to this talk. Yeah. One more thing. Yesterday I got an email that one of my students from the university got a COVID, and they did not tell who it was, and I did not even know whether I was talking to him at some point. I don't even know whether he was attending my lectures. But they asked me to double down on precautionary measures, and so thus I decided to talk in mask. I'm not sure it's because it will help, but the other thing that to be honest, I'm more comfortable now in mask because somehow it's better for me. I still can compose better if my face is covered, right? The last thing before I switch to mathematics, thanks a lot for the support. We need it, and we appreciate it, even though sometimes I don't know how to react to it. Okay, so whenever I'm talking on representation theory conference, I try to understand how much should I say about Jordan algebras. Because like everybody is familiar with Lie algebra, and you rarely see the definition of Lie algebra on any decent talk. But like with Jordan algebra, at least definition I should give. Yeah, they are coming from, originally they were introduced by physicists who were trying to find a new setting for quantum mechanics when you have Hilbert operators, which are actually matrices, but they are not, you have some conditions they are satisfying which are not associative, right? And physicists try to find a new setting, algebraic setting, where you have those properties, and they are hoping to find some place for those algebras to live outside of associative world. They actually did not succeed, but mathematician after that inherited some nice structure which has a lot of different applications. So a Jordan algebra is a commutative algebra with some additional condition of its partial associativity, right, which is called Jordan identity. And the most common example, if you switch multiplication the way you do it for get out of associative algebra, Lie algebra, but here you switch it not with minus sign, but with plus sign, right? So whenever, I have to just, whenever you use any associative or even alternative algebra, this product will give you a Jordan algebra. Most of the examples are of this type. Those are special algebras which are coming from some associative algebra, which live inside of some associative algebra, changing this product, are called special algebras, and those are usually main examples, right? So if you have associative algebra with involutions, then the subspace of Hermitian elements will be the Jordan algebra inside of algebra A+. And the second important example is if you start with the Jordan algebra, which is somehow related with Clifford algebra. It's called sometimes Jordan algebra of bilinear form or Jordan algebra of Clifford type. You start with symmetric bilinear form, and you add identity, and you choose your multiplication using this symmetric bilinear form, right? This algebra is also a special algebra. Actually, what happened to physicists, they were looking for non-special Jordan algebra, and they were able to describe all simple Jordan algebras over real numbers, and the only one which was non-special was what is now called Albert algebra. The Albert algebra, which is algebra of 3 by 3 matrices with involution over octonions. They were not able even to show that this algebra is non-special. It was shown by Albert, that's why it holds his name. It owns his name, and actually this Albert algebra was why physicists abandoned Jordan algebras, because Albert algebra was very single, isolated object to base on it the whole quantum mechanic thing. And yeah, but still, so we have plenty of special algebras, and then we have this Albert algebras. I will talk about it. So you have an embedding of this Jordan algebra inside of Clifford algebra, and this is just it, right? Okay. Representations. You can define representation from any class of algebras defined by identities, and the way to do it, it's by modules, but then since we have commutative algebra, it does not matter. Basically, the multiplication is commutative, right? So you define action on left and right, and then define a new algebra omega, taking as a space a direct sum of your algebra and this space with action, and then this algebra with respect to multiplication, this multiplication should be a Jordan algebra, right? If you do the same thing with Lie algebra, you will get exactly the definition of representation of Lie algebra. The problem is that, like, you will need to check that this algebra with the section satisfy Jacobi identity, and you will get relation for Lie algebra, right? In Jordan case, it's the same, but the problem is that Jordan identity is extremely nonlinear. There is the same variable involved 3 times, and if you try to linearize it, you get this. And to those who know how to work with universal enveloping algebra or with just a relation inside of associative algebra, you know that it's it's complicated to do any calculation. Just by hand, it's very difficult to use to work with this formula. In any case, as I said, when you define a representation of class of algebras defined by identities, you also can define universal enveloping algebra. In case of Jordan algebra, this algebra is, you just have to, you generate an algebra defined by right multiplications. So for every element, so basically you generate an algebra defined by a row of A, and then it is just you module out those ideal defined by this ideal generated by 1. Yeah? And here is the question. So as I said, you go from associative algebra very easily 2 ways. One with minus and the other time with plus. And why? So and you have, in one case you have Lie algebra, and in another case you have Jordan algebra. So why the universal enveloping algebra is so much more complicated in case of Jordan algebra than in case of Lie algebra? And the answer is the following. Lie algebra actually, because of Poincare-Birkhoff-Witt, is always special, meaning that you can always embed your Lie algebra inside of associative algebra with minus. So that's why what you get is very nicely defined. So you have here, this is, no, I don't, I think, so you see here, this is the analog of enveloping algebra, what you used to know about this Lie algebra, enveloping algebra, right? Here we have it for, if you just change plus for minus, and this 2 because of this 1/2 in front of your symmetric multiplication, this will be the analog of universal enveloping algebra for Lie algebra. Yeah? It called for Jordan algebra special universal enveloping algebra of J, and the relation with the whole enveloping algebra is here. So if your Jordan algebra has identity element, then you have such decomposition that universal enveloping algebra is decomposed in 3 in a direct sum. Here is a trivial modules. Here are modules on which your identity elements act as 1/2. And here is those modules on which your identity elements act as a 1. Yeah? And the reason that this algebra is not enough is because Jordan algebras are non-special. Not all Jordan algebras are special. You don't have Poincare-Bergov with theorem. From the other side, we are in different situation compared to Lie algebras because of the following fact proved by Jacobson. Whenever you start with with finite dimensional Jordan algebra, its universal enveloping algebra is also finite dimension. This minus to plus actually makes this difference. So you are talking about representations of finite dimensional associative algebra. That's why we are like using a lot of facts from representation theory of associative, finite dimensional associative algebras from quivers with relations, Dynkin diagrams and stuff like this, right? Moreover, if you start with Jordan simple algebra, your associative enveloping algebra will be semi-simple. So basically, you immediately get that simple Jordan algebras, finite dimensional Jordan algebras are all of finite type, meaning that they have only finite dimension, finite number of irreducible modules. And all of them are completely reducible. So basically, you only have to describe those reducible modules, right? Yeah, here I'm explaining that exactly that you can embed in this special enveloping algebra only when it's special, and we have this study. So basically, when we want to study category of Jordan modules, we have to study this category of special representations and this category of unital representation. Usually, this one is. So like, let's say that like if this is tame, this is definitely tame, yeah? And if this is wild, this is, so basically if this is wild, you don't even need to consider it. By meaning wild and tame, I'm using those terms from quivers, like when tame, you have to describe finite number of one parameter families, and if you are talking about wild algebras, you don't have methods, at least, to describe all. There are too many of those representations, right? So, like the special representations are there are few representations, let's say, and there are more actually. What we want to do? No, let me continue with. At least show you the case of finite dimensional algebras. All of those was done by Jacobson in 50s, and he basically used the properties of universal enveloping algebras corresponding. He constructed all enveloping algebras, both special and unital, and describe modules over. Yeah, it's then if you know the associative enveloping algebras, you know the modules, right? We have Albert classification of simple finite dimensional Jordan algebras. I only consider here the field algebraically closed field, right, of characteristic 0. And then you can, it depends on a number of idempotents. It's field for 1. It's of degree 2 for that algebra of bilinear form. You just have to choose non-degenerate form, and then it will be one algebra in each dimension. And finally, for when you have more than more or equal to 3 idempotents, you have those algebras. It's actually if you start with complex numbers, then you have symmetric matrices over C. Then you have so you consider you can put inside the composition algebra of dimension obviously 1, 2, 4, 8. 8 will give you exactly that Albert algebra. It only goes when n is equal to 3, and this is the only exceptional algebra among simple Jordan algebras, right? And for other dimensions, you have 3 families. It's basically symmetric, full matrices, and then symplectic matrices. If you just have to, it's always algebra with involution, right? And you consider the invariant, the set of invariant matrices with respect to this involution, right? For degree 2, as I said, like this Clifford algebra is important, so because it gives you the special enveloping algebra. Universal algebra is called meson algebra. It also probably comes from physics, and it's related closely to Clifford algebra, and one can construct. So this description of this algebras comes from, yeah, obviously here you have the Clifford algebra. It's either one matrix or two matrices. And for the, so you have the finite number in both cases, of course. As I said, always the special representations are less of them, yeah, and they are easily described and understand. This is for the case of degree 2. For the case of degree 3, you have, yeah, for the field it's easy, since I told you how one can, what are those modules? So you can act by one on with 0, with 1/2, and with 1. So you have 3 one-dimensional modules on which your elements act as 0, 1/2, and 1. And for dimension 3, it was shown by Jacobson that you actually have a functor from B module over your composition algebra to module, Jordan module or B module over your corresponding Jordan algebras. And so you see that these are the composition algebra of dimension 1, this is dimension 2, this is dimension 4, and this is finally the Albert algebra. And you can see it's exceptional, so its special enveloping algebra is 0, and it's, you only have this enveloping, this is a regular representation actually. So the only representation, reducible representation you have for Albert algebra, it's the regular representation. Yeah. Okay, so we wanted to continue we wanted to look into non-simple Jordan algebra. Of course, we lose immediately complete reducibility. We have to study indecomposable modules. And we started with the algebras of matrix type, of those with degree greater or equal to 3. And we started with a simpler enveloping, with a special enveloping. And we were able to extend this functor, this one, only for the case of special representation. And we actually were able to show that if you consider the special algebra, it will have a very important. So the class with which we started our consideration, the next step from semi-simple Jordan algebras was the algebras, those radical. In Jordan algebra, you have semi-simple part and you have nilpotent radical. So we started with radical, those whole square was equal to 0. And the reason for it was that the class of associative algebra with this property is very well understood from the point of view of representation theory. You can construct corresponding quiver, and this algebra with radical squared equal to 0 will be represented by a quiver with no relations. And it's very easy to describe when it's finite type of tame type, since it's related with Dynkin diagram. Or so basically, if it's written here, like if you start with associative finite dimensional algebra, whose radical square is equal to 0, Then you have that it is of finite representation type, meaning that you only have finite number of indecomposable representations if the quiver is disjoint union of oriented Dynkin diagrams. Yeah, yeah, double quivers. You have to, I mean, yeah, with double quiver you have to just if it's a quiver, yeah, it's double. You have one line of sources, you have one line of things, and then you just go. Here are sources. Here are. Yeah. So this is obviously will be the union of 2A3. So if you have original quiver with no relation, then it will be of finite type, and it's just easy to check it, and it's very nice property. So that's why we started with Jordan algebras with the same property, those radical squared equal to 0. And the main break, why we were able so easily to classify the whole class was because we were able to show that if you start with Jordan algebra with this condition, its radical square of its special enveloping algebra also will have this condition, will be equal to 0. And then you just pass to this criterion, and it's easily done, right? So it was my actually, yeah, one could say kind of part of my PhD thesis. So I started it very long time ago, and it was finished by publishing this paper in 2011, but then we were stuck because actually whenever, so if you go back to this classification, so basically we are talking about two classes, right? Degree 3 and degree 2. I mean, K is kind of easy dealing, and it's kind of was calculated on the first step. But then, so like we are talking about 4 enveloping algebras, special for 2, special for 3, unital for 2, unital for 3. So we only were able to do this special for 3 for algebras, those radical square equal to 0 because of this property. And then whenever I try to do it, because again of those relations, relations are worse in unital case, they're a little bit better in special case, but still it's a lot of computation, it's not very treatable. And then at some point I met Vera Serganova. I think it was like kind of the luckiest thing probably which happened to me as a mathematician and as a person. She's brilliant in all the ways. Like, I talked to her about this Jordan algebras. She's definitely a specialist in representation theory of Lie algebras and Lie superalgebras. And then we checked that there is actually not only bridge from Jordan algebras to associative algebras as usually with universal enveloping algebras. There is also another way to go. This was found out by, it started first by, first construction was by Tits, but then it was independently discovered and improved by Cantor and Köcher. If you go to Soviet school, they will name it KKT construction. I used to, if you look into my slides from 15 years ago, it was KKT. But then at some point, Olivier Mathieu, who is a student of Tits, he insisted, and we used also TKK in our work with him, so he's really insisting on TKK because of Tits did it first. Like, I think all of them did it independently at the end, but like, so I'm using TKK construction. And this is a way to build from any Jordan algebra, Lie algebra, graded Lie algebra, Z-graded Lie algebra, and get from some of the, you can also have it from Lie algebra, but not any Lie algebra. You have to have Lie algebra with SL2 living inside and producing this special Z-grading, right? So I will explain what this Tits Cantor Köcher construction mean. When Jacobson described representation of Jordan algebra, this construction did not yet existed. It was used first for Jordan algebras first from the point of view of classification. Jordan superalgebras were classified by Victor Katz using this TKK construction. Yeah, it was some, in representation of Jordan superalgebras, this is actually the main tool, or at least it is used there whenever you have a problem. Okay, I will go to this. I will tell about it a little bit. So how you construct it? You start with Jordan algebra and you introduce this commutative bilinear map P. And then you generate a Lie algebra where you have Z grading and you have what is called short grading when you have only -1, 0, and 1 part. You start with your Jordan algebra J. I only will be considering Jordan algebra with identity element. Usually you need, you can do it even without it, but like in my case, we always consider this construction. Then the 0 part will be left multiplication and what you can make out of it, right? And finally, the first degree will be those commutative bilinear map which you get using this P and this product which is defined here, the way it satisfies actually Jacobson identity. Yeah? This will be Lie algebra and it will be called the TKK construction for J. Let's do it just why it's always inside this SL2 algebra, because if you choose, as I said, you have to have this identity element. If you don't have identity element, you will have a SL2 action, but not SL2 subalgebra living inside. But in our case, if you start with identity elements, then those 3 elements, identity minus left multiplication by E with minus, and this P will become a triple which generates SL2. And actually, the eigenvalues of this element, they generate the eigenspaces of this H element, they generate your grading. So basically, you can start with, it's Z-graded Lie algebra, not Z. So whenever you start with Lie algebra with this short grading, it's Z-grading, and you only have 3 components. And you choose some. It's usually you have to choose. It's written here any element of G1. It should not be like any, but pretty much you can do it with almost any element of the first component. You can get a Jordan structure on a minus first component. Actually, it does not matter. G-1 and G1 will be, as a spaces, they will be the same. So basically, you can do the same. You can choose one element in G-1 and introduce in the same way a structure of Jordan algebra just using this product here. So this will be a Jordan algebra. Yeah, just before we go to representations, you have what is going on usually? You have, it's not one-to-one, because basically this G0 you cannot control. You basically have here, you have to choose whether you can put a lot of central extensions here. So you have the whole spectrum from you can add some conditions when it's the minimal one, and then you can have like kind of one-to-one correspondence. And this one, for example, what was used when Katz constructed Jordan superalgebras, simple Jordan superalgebras out of Lie superalgebras. For representation theory, we actually need the other algebras, the bigger, the larger Lie algebra we can get. Why is this? This is because first, like, yes, we have this Jordan B modules, and then we have Lie algebra with Z-graded Lie algebra with short grading, right? So representation theory of Lie algebra, you can see it even if you compare in universal enveloping algebras. So as I said, for Jordan, it's always finite dimensional. And for Lie, it's immediately infinite dimensional. And there are much more representation of Lie algebra than of Jordan algebra. If you start like with the matrix, the same matrix algebra, and then do it for Jordan way and Lie way, even just by comparing enveloping algebra, you see that there are more. And the same is here. So whenever you start with Jordan algebras, you get Lie algebra. Those modules theory is much richer. However, you still have, you can choose. You have modules with what is called, we call very short grading. So those, you have modules over Lie algebras, which with respect to eigenvalues of H, they decompose like this. And those will be, they will be, it will be the same category. It will be isomorphism of categories of special Jordan modules with this short grading. So, for example, if you start with field, as I said, then Cantor-Köcher-Titz will be SL2. And then you know very well the representations of SL2, and the only one which corresponds to this, yeah, you have to rescale a little bit of gradient, of course, but then you will have that what is called standard module, the module of dimension 2, right? The only one which will have this decomposition. And for unital module, we still need to consider modules which has the same short grading, so which have component -1, 0, and 1, right? And if you think again about SL2 case, so as I said, for Jordan algebra, which is just a field, you have trivial representation, you have representation on which identity elements act as a half, and this will be corresponding to SL2 standard module, and module on which K acts as 1, unital module will correspond to a joint representation of SL2, the representation of dimension 3, right? However, for the case of this, so basically what we have, remember that the composition of Jordan, of modules over Jordan algebra, you have, if you have identity elements, you have here the split. You can split it in 3 categories. And the splitting does not hold for Lie algebra, since you can have non-trivial central extension by module from this short grading, a trivial extension with central module. So here we don't have, if you don't have central extension of this algebra, or if you have, so if you, for example, it works for simple Jordan algebras and simple Lie algebras corresponding, it works very good. Here you can have actually one-to-one correspondence, and you can build one-to-one correspondence for irreducible modules, for example. It's not isomorphic categories in general, but still you can do what you can do. You can find a way to construct projective here, construct some quivers of category here, and then translate it here and restrict it only to this G mod 1 category. So this is our new way of dealing with it. Why it's better for us? So we don't need to work with associative algebras with a lot of relations and without a lot of with a lot of technical difficulties. We have Lie algebra. We have plenty of knowledge about representation theory of Lie algebras. And you have their weights, you have their tensor products, you have their characters, you have their cohomology, you have a lot of machinery which was developed and which is not available for Jordan algebras. I don't know why, probably it's still, for example, you cannot tensor modules for Jordan algebra, so you don't have tensor products. Cohomology theory is also not developed for Jordan algebras. We are trying to do it with Olivier Mathieu, but we are only talking for now about free Jordan algebra, so it's like very long way. So this for us was very good, for me at least it was very good way. So here, remember I talked about, here we have all the simple Jordan algebras of degree 3 here and 2 here. So here are corresponding TKK construction. You can see that those, of course, that's if you start with simple Jordan, you will get simple Lie algebra. And as I said, remember that it's very much fewer representations. So, for example, in the case of SP2N, this is standard, and it's dual for SL2N, standard again. Here you have spinor elements. You see SO appears for two different algebras, but the difference here is the grading. So you can introduce on those algebras a short grading in two different ways, which give two different Jordan algebras, right? And finally, you can see that, so if you're familiar with representation theory of simple Lie algebras, those are basic examples of representations. And for example, like in the book of Winberg, you have tables, tensor tables and formulas for all of this. Like we will need, for example, the tensoring between these modules, and it's easily, you don't even need to, you can just, so you don't need to calculate anything. You have so much knowledge and result about it that it actually makes our life much easier. Okay, so I still will be working with quivers. Yeah, before I was talking about quivers for associative algebras, right? Finite dimensional associative algebras, but you can do it for any abelian category with finitely many simple modules. Instead of, you can look into those which points of quiver which were idempotents, or again, you can call them simple modules there as well. And the arrows correspond to dimension of acts between those simple modules, or you can talk about homes between corresponding projectives, right? So what we look into, remember we start with the class of Jordan algebras, non-simple Jordan algebras with radical, those square is equal to 0. Then we go to corresponding Lie algebra, and then we try to construct quiver, corresponding quiver, and relations, representation of this Lie algebra, representations of very short representations or representations with short grading will be corresponding to representation of this quiver. And all those calculations we needed to do with constructing a quiver from universal non-developing algebra of Jordan algebra are now much easier, because so you start with this. So we started with this Jordan algebra. We go to Cantor-Köcher-Tit. It will decompose this like this. So like a semi-simple plus radical, right? Levi decomposition. And then if you start with radical square equal to 0, here radical square also will be equal to 0. And how you check what will be what are the arrows between two simple GS modules. This is exactly the multiplicity of L prime in this tensor product. So you have one of those modules which appeared here, right? You take another one and you take the tensor products, and the multiplicity of, so basically if you compare two points, you know immediately which points are connected by which arrows just by doing some tensor product of very simple representations inside of simple Lie algebras. So I start here with, so this is the Jordan algebra of bilinear form with this dimension, right? And I choose, I don't describe it here. I named it, it was in a list as a unital module. It was in a list of modules with the name Vn. So I just put it here. And the corresponding Tits Cantor-Köcher will be just this algebra where this is the standard module, right? So unital modules, like modules with very short grading for this algebra, will be the standard module and exterior powers of it, right? So basically the arrows here, they are obtained by multiplying this V by all these exterior powers, and if you, meaning that like if you want to multiply V by this square exterior power, you go to third exterior power and you go to the standard, and that means that how you get those arrows. For relations, it's more complicated. You have to construct actually projective modules for every simple module, and you have to. We are lucky because usually we only go. We need to construct 2 floors, right? Because filtration only has like 3, but like 0, 1, and 2 floors, and our relations are usually quadratic, right? So as I said, this is a unital representation, meaning that we start with very simple Jordan algebra, and you see this quiver, it's still finite, but you cannot you cannot go. Basically, we described this. Vera Sergano, we described all tame and finite unital modules for algebras with degree 2, radical square. Actually, we were able to get rid of this radical square equal to 0 only because they get wild almost immediately. We basically have 11 or 12 algebras which are tame. I don't believe we have any finite. And we only can add 1 module. There are no 2 modules in any place, so they are becoming wild really, really quickly. However, if you go, so I started with this. So now we described for, let's go back quickly. So we described for this special and for this unital. So we now have to deal with special for all classes, yeah, and unital for all classes. But those are the cases which are more complicated because here the first case was a simple one, right? This is one where we were able to prove that radical square is equal to 0. And the last case I talked about, it was really, really, it was simple to describe because it got complicated too quickly, right? And those 2 cases in the middle are where we, I would say, stuck for last. It's not stuck for last 10 years, but it's just like we are trying to find out how to classify. So we know all representations, we know all quivers, we know all relations. We just don't know how to, and we believe that there is very nice combinatoric inside, but we just cannot catch it yet, and we don't have methods which working with a general picture. So I have a lot of classes whereas I know which are finite and which are tame, and still some classes which I have to do. So you see, it's the same algebra. Here is a quiver for special representations. So just compare this one with this one. So, and of course, here it's you have a quiver of finite type for any simple module. If you just start with simple module here and simple algebra here, you have here some very basic and simple module, and then you have to start to glue them. So this category of special, which correspond to special modules, is equivalent to category of representations of finite dimensional graded quadratic algebra. So quadratic algebra are also very important for representation theory of associative algebra because it's class, a whole class of relations are very nice, and you can use different methods. And actually, we were able to show that if you start with, consider those Jordan algebra with radical square equal to 0, then its special representations they can be built out of the following blocks. It's not direct sum. We have to glue them. But what we have to glue, and we don't add new relations. So non-trivial relations are all here, and we have just to find here and here. So this is the only relations we have. Yeah, we have a lot of others. We basically have like all the kind of arrows without relations, and then we have to find out how to what finite and what tame we can glue out of those, right? And this is what we are still working on. Yeah. And this actually this was the first thing I asked Vera somewhere in 2010 for the first time, and we still are working on it. Parallelly, I wanted to use, I don't want to use the verb use, but like, let's say to use Vera knowledge about super algebras, since she's an expert in super algebras. And for representation of super algebras, as I said, the story was different, since even for classifying Jordan super algebras, TKK was really the main construction which Victor Katz used to describe Jordan superalgebras. Here is the list. I'm not going to define them because it will take another half an hour, right? The construction TKK works the same way. You still have the same relation between Jordan superalgebra and Lie superalgebra. You have a central extension. You have kind of list of algebras between this universal central extension and like the minimal Lie superalgebra there. And if you're talking about minimal, then you can have, this is the list. This is a correspondence. This is a correspondence Katz constructed, except for, I believe Katz means this family, which was then corrected by Cantor, and that's why it's Cantor family. And I believe there was some problem with case 3, which I did not even list here, which is Kaplansky superalgebra, and it was done, I think, found by Kaplansky. Probably it was some error in Katz classification. Okay, so for representation theory, it started by the first works were done by Stern. He did it for exceptional algebras, and he used Cantor-Köhler-Titz, but he did not do it using the central extension. He did it just like from minimal to minimal, and actually his answer for Cantor is not incorrect because he forgets that, I mean, he did not prove, he did not have those theorem about relation between very short grades. He used those modules, but he did not know the fact that you have to consider the central extension. Then the most of the classification was done by Consuelo Martinez and Yefim Zelmanov for this matrix algebra, so Frank greater or equals than 3. They used associative methods, the methods which are close to the case of Jordan algebras, and those algebras are also when you have greater indices starting from, like, you need to have at least 3 idempotents, right? And for them, you have the situation very similar with algebra case. They are finite dimensional and semi-simple, and you have like description of those modules which are close. You can get them from modules of a corresponding associative enveloping algebra. They also have shown that this is a bilinear form, super form in this case, this one. They have described reducible modules, and then Vives Vera showed that there are no indecomposable modules, finite dimensional, because they did not answer the question whether it's completely reducible. And also they were able to describe the case of Q2. So those here 2 cases, they are finite dimensional, meaning finite of finite type, meaning that you're getting finite number of irreducible representation, and categories are completely reducible. For these algebras, Martinez, Zelmanov, and Restakov, they showed that they have infinite number of reducible super B modules, and actually all these algebras are not completely reducible. You have to consider indecomposable. The same is also with this algebra, which was like, it was done by Stern, but I think I pointed out to Yefim at some point that actually there is an error here because he did not consider central extension. So you have a list of 5 algebras where you have to consider indecomposable. First two were done by Martinez and Zelmanov. They describe the list of undecomposable modules over K3 and DT. And they actually they did something on JP2. They were able to describe all undecomposable modules over JP2. No, they described all indecomposable modules over K3 and DT, and they described all reducible over JP2. And then they were not able to describe indecomposable because it started to be a lot of them. So actually, we found out when you look into the quiver, so this quiver will be wild. So basically, even though we described them, we don't have very good description because there are too many. We're still describing all of our algebras as a quiver, right? So we were able to do it with Vera using this technique of describing a corresponding category of Tietz-Cantor-Köcher construction for the superalgebras. Yeah, I probably will try to do it, still do it. I have 9 minutes, so let me. I'm talking only about JP case. JP2 case I will be, but just I will introduce this JPN algebra. It's superalgebra, which is symmetric elements with respect to the following convolution. So you can describe it if you know PN algebra. It will be PN Lie superalgebra. It will be its Tietz-Cantor-Köcher construction. Here, so they are, I think the difference is with some minus sign in the description, right? Yeah, so it's here, you can see it here and there, right? For JPN, for n greater or equal to 3, Martinez and Zelmanov presented 4 unital irreducible B-modules. They showed that when n is greater than 3, it's completely reducible, and it's greater or equal to 3, it's completely reducible, and one don't need to. So you have those modules. They are, one of them is regular, and the other one they constructed. They call it P n minus 1, and they're opposites. How they showed it? They kind of also use this bridge to Lie algebras. They show that corresponding Lie module decomposes in a direct sum of certain eigenspaces with respect to certain Cartan subalgebras. And using weight arguments, they show that there are only 4, there is only possible 4 irreducible modules, unital modules for these algebras. For the case of why it does not work for any n, it's JP2. It's Tietz-Cantor-Köcher is P3, but then, as I said, you have the whole possibility of central extension. In this case, this algebra has non-trivial one-dimensional central extension. So you have to consider representation over this algebra. And this means that you have new parameter, which usually is that action of center. Your center acts on Lie algebra with some as a sum value, some parameter, and then this is what gets you irreducible families of Jordan modules when you go back to Jordan algebras. So they show that you have not 4 irreducible, you have 4 families of irreducible modules. Unital irreducible modules was the case of these algebras, and they were able to give a realization using some while algebra and differential operators, and basically they realize it as a submodules inside of this algebra. So construction I, for example, did not understand, and so when we started to, so here are still only reducible. How to go to indecomposable? We actually we only use the fact that there are only 4 families. This we still used. Yeah, but how we classify, we found a new realization of irreducible, and starting from them, we constructed indecomposable and quiver of corresponding algebra. We use the following grading. It's quite known for P3, and you have it, this grading, it's consistent with supergrading, and it's also consistent with short grading in a sense that you are No, I don't. I actually don't remember now whether it. I think it's. Yeah, it is. Yes. So this is. It's not the same grading as the Tiskantor-Köcher grading, but you have a grading which is consistent with super grading. G-2 is one-dimensional center. You have G0 is isomorphic to S6, and G-1 is a standard SO6 module. And then we were able to find a module on which we constructed. So this is the representation which will be P3 head module. This actually will correspond to its, and its dual will be not dual. It's if you change its parity, you will have two families inside of special representations for P3. So any simple object in a category with very short grading is isomorphic either to VT or VT opposite when you just change parity. Every block in this category has a unique simple object, and the category is equivalent. So basically, you have the quiver with just point and yeah. So you have a family which depends on one parameter and category of finite dimensional representations of a polynomial ring CX. And starting from these modules, we constructed, so you see here you have 4 families of reducible finite dimensional modules, and they were realized as a submodules of this algebra. We have them in the following way. We just tensor product these 2 families, and you have S2 symmetric square and exterior square, and those will be exactly objects in unital, will be modules with short grading, which correspond to unital modules over our Jordan algebra, and those are exactly the families, and I think these are much better realizations. Those algebras and those modules and these modules with the change parity. And they all will have, each of them will have central charge T. So we have this new description, and now we can construct indecomposable modules as a quiver. So this is the quiver here. So we have, first of all, category decomposes into direct sum of based on a value of this central charge T. Each category has 2 equivalent, for each T, this category has 2 equivalent blocks. One is with S2V lambda S square and lambda square, and another one with opposite, yeah, with parity changed. And you have the following. So these representations are represented by this quiver. Unfortunately, it's wild. It's not tame. So basically, you still can describe representation, but you cannot classify them, meaning there are too many representations, right? But at least representations can be described with this quiver. And the only thing that the main problem working with Lie algebras is because you done all this for T different from 0, and it's much easier for when central charge is different from 0. And for T equal to 0, you have to consider, it's at the end, all what we have, all calculations we get, we always obtain the same result for T different from 0, T equal to 0. But the situation with T equal to 0 is more complicated because we always have extension by trivial modules. We have to have at trivial modules because for T equal to 0, you can extend your module with trivial extension. You have to calculate more relations. And then when we're passing to Jordan algebra, we still have the same module because this is a module for Lie algebra, Lie superalgebra. And we have to remember to go back to Jordan when you have to take out this trivial point which corresponds to trivial module, right? So at the end for T equal to 0, for Jordan we have the same quiver as this one. And we are thinking that we're probably missing something, and we have to find some way to do it for both T different from 0 and T equal to 0 in the same way. However, we don't know how. For us, this one is more complicated, and it's a pity that it's always the same at the end for Jordan and different for Lie superalgebras. But this is the price we are paying for using the machinery of Lie theory. Yeah, it's Right. So that's all. Thank you. Yes. There is no so first of all, the nice theory, for example, those Dynkin diagrams, they are those nice criterion for double Dynkin diagrams and Dynkin diagrams. They are only working in characteristic 0. There are some results by DLAP, I believe, in characteristic different from 0, and you have to start to deal with non-simply laced Dynkin diagrams. This is one thing. The other thing, there is no Cantor-Kocher-Tits in characteristic different from 0. So I'm stuck with characteristic 0 from different points of view here.